Oh, okay. I thank John and Brian for organizing this workshop and for inviting me to have a talk about our experiences and our thoughts about the need for metadata if we want to archive raw diffraction images. Okay, some of these thoughts have already been mentioned by John. There are reasons for wanting to archive raw data. As a first step, to allow reproducibility of the science. That's what we always want to do in science. We want to be able to reproduce other one's experiments and see if the data are really that are coming out of this are really valid. We want to safeguard against error and fraud. It's clearly much harder to fake raw diffraction data compared to processed data, as we know. However, in the end, that also is a possibility. We want to do further research based on the experimental data, and we could do in future comparative studies. We want to allow future analysis with improved techniques, changed standards, for instance, the resolution cutoff, to give an idea, and we want to do new science, which we didn't think of before. Also, these images could be very useful for teaching. Okay, so far we are used to storing processed data. Crystallographic structure determination usually starts with the integration of black spots, and a lot of decisions are already made there. In the end, we then get the integrated intensities, and we do a structure refinement against those to the structure factors that are again derived from the intensities. So this is really derived intensities. In addition, we use prior knowledge about the structure and in the refinement. Then the protein data bank is very important in storing all these derived data and the results, the final coordinates. So it's a big step forward that derived data actually stored in the PDB. And also it's a requirement of the PDB that there is an associated publication, which also gives a lot of, let's say, metadata information. What this resulted in storing the derived data is that it is possible to do a systematic reanalysis of all the structures in the PDB, like, for instance, the PDB redo project. Now imagine, let's first say what additional information to the integrated intensities is in the raw data. There's information about the detector non-uniformity, the spatial distortion. There's information about the background scattering and hopefully also the detector gain. And if we have access to those, or look closer into those, we can allow reanalysis of the standard deviation of the integrated intensity, etc. So we have a much more open, in-depth analysis if we have access to those. Then John also mentioned shortly the symmetry. The researcher decided that the reciprocal lattice has a certain symmetry. He merged the data accordingly and went on with the structure determination. And there is this initiative now to store the unmerged data so that later on people can still see if the symmetry is correct or not within the standards you have for it. Then the shape of the spots, they depend on a lot of things, for instance, the crystal size, the divergence of the beam, the mosaicity, the particular lattice. And you can imagine that in future, or by reanalysis, you can do a better spot integration. Then there will be composite patterns, twins, triple lattices, etc., that have been overlooked by the researcher or maybe ignored, but it's still there. Then there's the scattering between the spots. Diffuse scattering is growing in importance, growing in interest, and diffuse scattering can be streaks between the bragg peaks that are a sign of packing defects, or we can have what we call variational diffuse scattering, which is an indication of protein dynamics. Then there is the incommensurately modulated or composite structures, where you have actually satellites between the reflections. And again, you can ignore those or try to determine a commensurate lattice, a superlattice, and try to solve the structure that way. Clearly, for methods development, it's very important to have those kind of data available. Also, raw data may allow you to come up with a validation scheme or criteria for how to integrate your data. So you should look maybe better at the background or what you leave behind if you do an integration. And then there are, of course, the data that didn't lead to any structure determination, that is still lying somewhere. There's no associated publication. These cases would be very useful for methods development. Later in the workshop, there will be a talk by Michael Wohl about diffuse scattering. So this is very interesting, potentially. And it may happen that these data are lying in the drawer somewhere of the scientists that couldn't solve it, and they are lost forever, which really would be a pity. Now, I ask myself the question, and it may be that we should all ask this, what would be needed with respect to metadata if we would like to run a project like PDB redo on raw diffraction images? So a fully automatic reanalysis of all the diffraction data. The first thing you need is, of course, a well-documented data format. It doesn't necessarily have to be one specific format like CBF ImageSIF. Could be anything, but it has to be well documented. And if we want to have long-term preservation of the data, we should have sufficient metadata to allow that. To allow the discovery, because it's useless if in the end you have stored all the data in an archive, but people cannot browse through it or search it. And we should be able to reinterpret and reuse the data. And I want to talk about what is the current status. One initiative that I would like to mention, and there are many more of those, is the Diamond Light Source and the ESRF have a data management system, ISPyB, that actually manages the data that are collected at the synchrotron, and the data analysis is automatically performed. So basically you get processed data, and also normally you would get the structure out. So then you know that everything, all the information to do this was there. Now, scripts with metadata are provided for instance, Mosfilm, XDS, the standard packages. So that contains sufficient metadata to do the structured data analysis. Now, the user is then in the end responsible for taking the data home, to transfer the data, and also for the backup. It's not a policy yet, at least for those synchrotrons, to have an archive of all these data. And then we have to ask ourselves, so once the data are in the responsibility of the user, will he retain or have sufficient metadata that in the future the data could be reused? Then I wanted to talk about our own experience with making image data available. John once contacted us. He had 11 lysozyme crystals, different type of crystals. He collected data with 2 diffractometers, 2 different equipments, highly redundant data, and they were originally processed with their own equipment's software. And there were differences between the structures, and he wanted to decide if this is a software problem or a hardware problem. And therefore, he wanted to use just one software platform to process the data. And Eval was one of the software packages that could do that. So the data were transferred from Manchester to Utrecht, and it was in total about 35 gigabytes of uncompressed data, and that took about 30 hours to transfer, and it actually took several days to get it done. Once the data were in Utrecht, they were compressed using ncompress, which is a lossless data compression-free algorithm, and then the data took 20 gigabytes. And the advantage using eval is that you can actually read in compressed data, and the data are uncompressed on the fly. So that's very convenient. The Bruker images, we had the Bruker and Rigaku images. Bruker images were in native U8 format, a single byte format, which is very efficient if you have not too high intensity pixel intensities. These were unwarped in Manchester and later in Utrecht using what we call the P4P file, which contains a distortion table. They were then written to Mosfilm format, so-called Mosfilm format, using frame utility of Bruker, and that's a 2-byte format. And it turned out that we couldn't read it in eval. And in the end, this was actually an error of frame utility, because it did write the end of the header at the wrong position. Now, we corrected this by Python script, so in the end we could read those. And it has been communicated with Harry Powell, so that is, at least Mosfilm now can read those as well. Okay, we decided to put our data on an archive. And we first thought that Manchester University would take care of that, but that took a bit longer than we wanted, really. So therefore, we decided to set up our own website in Utrecht, raw data UNL. And here you see the overview of the data we have. There are several options here in, well, let's say the central part is the tar files, so you can get all the data. But on the left side, you see a link to a single image, so you can download this single image and try if your program can read it, if you understand the image format. Then there's this PNG file. You can look at an image, the way we have interpreted such an image. And on the left side, on the right side, which we thought was very useful, is a photograph of the experimental setup. Because if you're a software trying to decipher images, it's very useful if you know what's up and what's down and left and right, and what the goniometer looked like, and where the beam stop was located, etc. So that's why we have added those. Okay, we have on this raw data site, there are about, during those years, since 2013, 150 gigabytes were retrieved by whoever, but at least Kai Diedrichs, in the later, we have an additional set of those data. Kai Diedrichs downloaded these and he reprocessed the 3 data sets. And from that, we came into analyzing further the anomalous diffraction data in it. And that was very useful, and we actually made a publication together with him about this. And in the supplemental to that paper, I have a discussion with Kai and with Twan Scheurs, who is our software manager, about the Bruker-Gai goniometer, because for him it was not straightforward how to interpret this. And the reason actually is that there are rotation axis is sometimes not perpendicular to the X-ray beam, which was not what he was expecting. Okay, then there was another set of data downloaded, which actually is the reason why we have this data set, that some people download those data sets, like Chabelin et al., and reprocess some of the data. It's very interesting that they have an interest in the cisplatin binding to histidine studies, and it can only be very helpful. As I said, we set up this raw data archive, and we are the first, I think, to link a publication in Journal of Applied Crystallography of this analysis to the raw data. So actually in supplementary material, there's this link to the raw data here. And these are now, in the end, pointing to Manchester, because after 1.5 years, they finally set up the archive system in Manchester. So if you click on that link now, you go to the eSchooler archive at Manchester Library. You see here, there's this data set that has the PDB code for DDO. And on the right side, you see that the data have got a DOI. So the data have now a DOI. All of these data sets do. And you can find them locate them in this way. And also, you have again those images data sets available. At the bottom of this supplementary material, you see the link to the raw data archive. So it's the one but last in Utrecht. And also at the bottom, you see a mirror data of TARDIS. If you click on those, you go to TARDIS. And you see that those data were also stored in the TARDIS Store Synchrotron archive, which is we will hear more about later in the workshop. Okay, a short overview of what the general purpose repositories actually provide an option to store raw data. That's dry it. It is used very often by many journals to store the supplementary raw data to the paper. For instance, Nature and Science use those. And you get an own DOI, and the maximum number of gigabytes you can store is 10, so that's not too bad really for a normal data set. And sometimes the charges are covered by the journal, sometimes you have to pay yourself. There's also Figshare, which is cloud-based, and data get also a DOI, and it can also be used by publishers to host data for online papers. So this is an option. Then there's Zenodo. That's an EU-funded open-air project, and actually it uses the cloud infrastructure of CERN, a Large Hadron Collider. And last year I've been searching for diffraction data, and now in the meantime there are more data there. I get 15 hits, and 6 of these are protein data sets. So it's being used, let's say. Then there's Dataverse. It's used by many libraries, university libraries, for instance. It doesn't have DOIs, and you can potentially get a lot of data on there. Though, for instance, in Holland it isn't. You can only have limited, so that's about 2 megabytes of data. So there are possibilities to have general purpose repositories. Then there's diffraction data repositories, specific ones. The overview has been given by Steve Andriakis in his paper in this metadata, in this raw data series. There's the University of Queensland Diffraction Image Experiment Repository, which contains 37 data sets. Then there's the Joint Center for Structural Genomics. They have stored all the data, there's many of them. And there's the TARDIS Store Synchrotron. And they store all the synchrotron data, and after a period, and on the wish of the scientists, they can be made public. Okay. I looked at the metadata that go with those, and this is usually very limited. For instance, in Dimer, you have this little table here that, should tell you what the data are, and if that is enough information, I doubt, and we will see later what kind of problems you can have. Of course, in a way, a publication and a PDB entry is also metadata. You can find a lot of information about the chemistry, as Jon said, of the crystal. So, what is our experience with the level of metadata? Here is an image header, the way we interpret it from an R-axis, so the Rigaku format. And one of the things I've mentioned here, in the red circle, that the spindle axis actually not defined, it's unknown, it says, and also the direction of the X-ray beam is unknown. So this means you have to guess or you have to know how the setup is. This is the Bruker format. It's rather well documented. I hope you can read it. I guess I hope it comes across in the transmission. It's well documented. For instance, there's the beam XY positions in pixels. I will later discuss that is not all. The wavelength is there. Then there is the number of, let's say, the pixel size, which you have to infer from the number of pixels per centimeters if you would have 512 pixels. And if you don't, you have to recalculate this. So it's not straightforward. Here is the angles. It's a 4-circle goniometer. And we have 4 angles, let's say, so the swing axis of the detector, 2 theta. We have the omega, the phi, and the kappa, the chi axis, which is set by a kappa goniometer. And there's an entry for the unit cell, and that's because in the Bruker software, Apex or per team, you can determine the unit cell and determine the structure actually, and you could insert the unit cell. And that could be a very useful thing if you want to, if you have once processed the data, you could insert a unit cell, and that could be helpful in the end as metadata. On the top there's the type of goniometer, so that tells us what type of goniometer it is, and then you know where all the goniometer axes are. Then another one item that is important, that's the gain, which we have to infer from 2 numbers there, and the result is that the gain is 3.8 ADUs per X-ray photon, and that's useful for error analysis. So if you, the square is the square root, the square is square root. So normally you use the gain in trying to estimate the standard deviations, because we start out with determining the standard deviation from Poisson statistics, but that only holds if we are really talking about X-ray counts. And you can convert to X-ray counts if you have the gain of the detector. And then you can try to determine the standard deviations. If you don't have these, then there are still ways to estimate those. For instance, from the internal sigma at the bottom there, we just compare reflections that should have the same intensities, like symmetry-related reflections. And you can also try to determine from the background, where you have the intensity is, let's say, following a Gaussian distribution, where you have the sigma squared divided by the average intensity, should be the gain. Now, this is often not the case because you have a lot of correlation between pixel intensities. It's a paper of Waterman and Evans about it, all the propagation of errors in data collection with CCDs, for instance. So this is not the best way to do it. So really, we would like to have access to the gain. This is Pilatus 6M header. Actually, Pilatus uses what we call a mini CBF format, which is simply an ASCII header. So it just ignores all the possibilities that are in ImageDiff. It just writes a plain header. And I hope you can read it. It says beam xi and it gives pixel coordinates. But it's not clear where the origin is. It's not determined. Then there is a starting angle, it says 110 degrees. But what axis is it referring to? And there's polarization. Which plane? Well, it's usually synchrotron. You know a bit about how that is set up. And in eval, if it reads those kind of things, it determines that it's so-called horax goniometer, horizontal axis goniometer, which is normally the case in a synchrotron. So, what metadata do we have to store our raw diffraction data? And I found that the header contains usually very limited information, and if it does, it's usually in the context of the equipment of the beamline. So if you know how it's set up, then you know what it means and you can interpret those data. The goniometer, These days, usually a synchrotron installation had just one spindle axis, but more recently they also have a so-called mini kappa goniometer, so that plays a role again. So if you have a goniometer, you should know where the axes are, what the axis orientations are in lab space, and what the rotation directions are. We should know the 0 positions, because if you have 2 goniometer axes, then that it really matters. And you would like to know what type of scanner it was. A continuous scan, still images maybe, a helical scan, and what the oscillation range is. And here I've written the 8 type of goniometers that EVAL can recognize. And you can see that the definitions of axes, for instance omega, can change from goniometer to goniometer. Sometimes it's the z-axis in our definition, and sometimes the y-axis. Sometimes the rotation directions changed. For instance, compare the kappa goniometer, which was the Nonius one, and now we have the x8. It's the, let's say, Brugger way to define it. And then the rotation direction of omega has changed, for instance. So it's going the other way around. It's the positive direction, it's the other way around. So these are, let's say, what we call prior knowledge. We have to know how to interpret all the goniometer angles if you want to process the data properly and not having to think too hard to get around it. Then about the detector. Well, it would be very good if there would be a type and a serial number. Maybe you can learn from this typical detector. Then the data format should be clear. So you should know the byte storage architecture. I guess this is not the biggest problem. We should know how to handle overflows. I mean, there is always a provision in such data formats for overflows. And you have to know how to interpret these. There could be a baseline offset, you have to know that. And as I said, the gain would be very nice to have. Is there a swing axis? What's the distance? That's clear, that should be in there. And then we have this problem with the fast and slow running pixel coordinates. In what direction is the horizontal and the vertical axis? And the origin, is it lower left, lower right, upper left, etc.? That's things you have to know. Fine. Okay. And then you need to know which corrections are applied to your raw images, because the raw images very often are not really raw. They are already in a way processed. For instance, the dark current can have been subtracted, distortion was already corrected for. It's usually manufacturer applied. The non-uniformity could be already applied for. So you have to know these. Then we need to know the beam properties, the position of the primary beam and the divergence of the beam in 2 directions and polarization. It would be very useful to have the photon flux, exposure time clearly, number of repeats. So very often images are repeat to get away with to skip zingers and that sort of effects in CCDs. It would be good to have the dose, and of course the wavelength and the dates. Then there is more, let's say, information that has to do with your sample, the crystal size, for instance, shape, the chemical composition, heavy atom derivatives that have been used, multiple wavelengths that actually group data sets together, they belong together. And those kind of experiments on just one single crystal. Sample mounting can be very important, and I'll give an example on the next sheet. And we would now like to have a name or identification of the sample we have. That's what John called the chemistry of the sample. And we would be good if, let's say, the researcher already made the classification. This is a diffraction of a single crystal, twin, diffuse. We saw diffuse scattering. That would be very helpful in searching for the metadata. This is an example of where it would be useful if you would know the setup. So that's why I say a photo could be included. And this is a scan where the rotation angle is not perpendicular to the X-ray beam. but actually skew, so it was pointing in the direction of the detector. And it was, the sample was mounted in the capillary. And it was copper radiation that was used, so glass capillaries absorb copper radiation quite significantly. And you see here the beginning and the end of the scan. You see in the top view the greenish yellow image. So we have at first the capillary pointing in that direction, and at the end of the scan it's like this. And if you look at the top image, where it's actually video of the top part of the detector, you actually see a shadow of the capillary, and also you can see that there is the hole in the capillary where reflections come through. So you actually see the end point of the capillary, and it doesn't, if the reflections are skewed to the capillary, they don't get through, but if they happen to be exactly along the capillary, they sneak through the image. So this is a very surprising thing to see if you don't know what the setup is. So metadata should be machine and human readable, I believe. A way to do it is the image SIF format. On the next sheet I will show you why. Or alternatives like ACF5 nexus trees. I'm sure that we will hear talks about it later. And the setup of photo of setup is very useful if you look close into the data, but for high throughput this may not be useful. Here I've compared the header of Brooker Smart format and that of CBF. Now I'm not sure if you can really read this. So here, for instance, you have the diffractometer angles of the kappa goniometer. And if you wouldn't know which angle is which, you don't know how to interpret this, because that's not actually given in the Brooker header. It is in the CBF header. So this actually was a conversion that was made by Brooker, Jörg Kercher, so they did a very neat job in being able to convert to CBF. Here actually is the definition of the goniometer, where every axis, omega, phi, to theta, have been defined. So you know actually where they are in lab space. So that's a very neat way to do it. And further on, later, you actually get the values for those diffractometer axes and rotation angles. So this is all very well defined. So even if you would know nothing about the setup of the Brooker goniometer, with the CBF you simply could interpret this. Yeah, these are the starting angles. These are given, of course, in Brooker. And here you see that the rotation axis is axis number 2. So you have to know what number 2 is. Then there's a little thing that maybe is not such a big problem. But for instance, if you have a Pilates image, you see in between the panels, you see strips that didn't collect that there is no phosphor. And they are given the value -1 in these images. And if you look at the ADC images, they are given the value 0. So we have no standard for doing this. On the other hand, there are many tools and programs that automatically can determine these, because it's so, let's say statistically, these values are so much off of their environment that you can recognize them and make a kind of mask for it. And this is the final example where we got data from Ergon National Lab, Beamline 15 IDB, where actually they have the setup, as you see in photographs, where in fact the whole goniometer has been rotated 90 degrees, so that the beam stop, as you see it here, comes from the bottom, which is very unusual, because we assume that in synchrotron we have still horizontal polarization. That means it's an unfortunate setup, because usually then you would take the rotation axis also horizontal. In this case it is vertical. It's here. But that means you have not made full profit of the polarization you have. And you have to know this. you have to understand what actually happened, what the setup of this diffractometer was, to decide on the right polarization plane, really. So that can sometimes be complicated. So to summarize, I believe that in the long-term data preservation and future use requires that we have detailed and very strict metadata policies. Otherwise, we will still rely on knowledge that is around in software engineers or in software that will allow us to read the data, but you cannot hope that in future this will still be the case. And it's very practical if it's machine and human readable, could be searchable very easily and discoverable. So I believe that is what we should do. Thank you for your attention.
Thank you very much, Lo. It was a really great start to the workshop and very comprehensive. We are conscious of coffee waiting for us, but let's take a couple of questions.
I mean, situation with frame formats and header formats, it's much more complicated. Because Mars 345, very popular in Europe, image scanner, has 32 frame formats. Can produce 32 frame formats, and software has to recognize that. Our Axis produced different frame formats for Europe and US and different for Japan. And with Araxis 2, with Araxis 4, you have several frame formats. With Bruker detector, there are also at least 2 SFRM formats, and I'm not sure if companies really realize that they produce 2 frame formats. And the same, and CBF, it's again, CBF is not CBF format, it's another frame format, which is different on not on every bin line, but I know at least 4 or 5 different CBF headers. Yes, and you can automatically recognize them, but it's a real mess. And 27 years ago, when I joined protein crystallography, or converted to protein crystallography, I was invited for a workshop which was supposed to unify headers. In 27 years, and in that time there were 5 or 6. Now we have, I think, 192 frame formats, if I remember correctly.
Yes. I completely agree. This is the situation. It would be great if everyone, all the manufacturers of detectors and diffraction equipment would adhere to a single format, CBF or ImageSIF or whatever. It's ImageSIF and CBF. But that simply doesn't happen. They stick to their own way of devising formats. I think most of the manufacturers really have it well documented. Even though they have different formats, it still gets a kind of format number. So you can decipher from it which format it is. But as I said, if you have all those subsequent formats and such different dialects, then you have to integrate it in your software, like HKL 3000 or eval or any software. You have to cope with it, and that's not very fortunate. It would be much better if that would be clearly defined, and that at least the header would be in ImageSIF.
So let's break for coffee. Otherwise, we won't have any coffee that's warm, hot. So we'll thank Lowe's again for a really comprehensive first start to the workshop. Thank you.